we're going to apply some of the techniques of matching and estimation that we looked at in the first lecture to a very famous data set. So if you've got the notes there with you. Okay, so the paper here is by Lalonde 1986, and it uses some experimental and other data in the 1970s where there was a national support worker program. So disadvantaged people, so for example people that had been in prison or had maybe been drug users or had lost their jobs or were very poor, were eligible for a program where they were given paid work, a place to live, and they was given quite a lot of support and training. There were two different settings. So one, most of the people that were assigned to the worker program, they were selected because they were the most disadvantaged people. So there was some people, most people who had the program self-selected into the program. So we already know to begin with that if people are selecting into this program, that it's most likely that they're going to come from disadvantaged backgrounds and that they're likely to already be earning low anyway, so that we'd expect possibly to find people that had the treatment actually were earning lower than people that didn't have the treatment. So it's not that the National Support Worker Program wouldn't increase productivity and their earnings, it's that the people that would select into it would of course on average likely be less skilled and so on to begin with anyway. So Lalonde gets around this by using experimental data where people were assigned at random. So using this data where people were assigned at random, he found that the treatment, namely being assigned into the National Support Worker Program that helped disadvantaged workers, actually increased future earnings by around $900. And they found that this was a statistically significant effect. So this is this here. So the paper looks at, the part of the paper mainly was to compare what we would find if we had experimental data where we had random assignment compared to what we would get if we didn't have this and we had to use data where people had selected into the program. So the experimental data, which was assigned where people were assigned into the program at random, found a positive effect. And we'd expect this, right? We would expect people that were given this training program and were given a job and support, it should really increase their future earnings. He also, as a comparison, looked to estimates from non-experimental data from the panel survey data in the US, which gathers, it's a survey where they gather data on people's income and their age and their health and so on. And within this data set, it had whether or not people had applied and had gone on this National Support Worker Program. So the difference with the survey data is they weren't assigned at random. These people self-selected into the treatment. So we should expect when we use this non-experimental data, which is data that we econometricians normally have to use, we may expect that we may get something different than the random assignment data. And what we're going to see here is that even if we use matching techniques and try to compare like for like people, we actually find that there's a negative impact of this training program. So this would mean basically that we haven't controlled for all of the factors which people use to select into the treatment. So if we find there's a positive effect with random assignment, well, we know with random assignment there's no selection bias, so we can be quite confident that this should provide a good estimate of the causal effect. So this is telling us then, it brings to light that when we use non-experimental data, we have to make a lot of assumptions and they may not always hold. Namely, even when you can control for age and past income and education and so on, we may not have controlled for everything which governs whether or not someone selects into treatment or not. So we're going to focus on this non-experimental data, but if you want, you can read the Lalonde paper and it goes through the experimental data as well, and you can also find this data online. So you can also replicate the findings in the paper by finding the data yourself. So to begin with, we're going to go through a number, and just to be clear, what we're going to run through in this live stream is not so much that we're going to replicate the results. It's more to see how can we use these techniques and how do we actually estimate them and compare them. So this here is for your own benefit. If you want to replicate what we've done in this live stream, these are all the commands that we're going to use. These are all the commands that we're going to use to reproduce the data, to reproduce the outputs in these slides. So we're going to use the new PSID data. There should be an underscore there, which is a D. This is the NSU PSID.dta, which is in the week 1 folder. So to use data, you create a folder, give it a name, put your data in there. Then when you go into data, you change your working directory and you change it to the folder where the data is. Then when you click use this data set here, it will then load the data into the program. So we can see here then, it's done 2 commands here. So there's a command, the command history is here on the left. So as we go through the commands, they'll get added as we go down. We can see firstly, we've changed the directory. So we've saved, in this case, I just saved the data into the desktop, and you can then change directory. So cd is change directory, this is a command, and you put it within these hyphens here. You can actually, instead of typing it out simply, you can go to File. If you click on File from the drop-down menu, there will actually be an option to change it directly by using the interface, and you can just do it with the mouse. So it's actually quicker just to select the folder using the mouse. You then change the directory. So in the directory, we've got this data saved. So we're going to use, the command is use. This is the name of the DTA file. This then loads the data in, and this clear you can just put in, it just clears all previous memory from before. So any variables defined earlier. It's not usually a problem when you start a new workspace, but often we just clear, so it clears all the working memory. Once we've loaded the data in, so this in essence loads in the data then, it then opens these panels here. So this here is a definition, it's all the variables. These are the variable names, and these are their labels here. So we've got the variable name and we've got the label. So you can look at the properties of these individually. And it also gives you more information down here on the properties of these variables. It's got the name, the type of data, but really this is the interesting part. And you can often you don't really need this properties panel. Often you can just delete this and click across and take this panel out. Okay. So we then want to, normally when you're doing statistical analysis, we want to look at the data. So we've loaded a data set in. So again, you can go onto the website linked to the Lalonde paper, and you can find all the data sets there in data form that were used in the paper. So you can, if you want, normally you want to screen the data, so you can start by looking at describe. So the command is describe, and we can see this is the next command here. So this is command 3, and it prints the beneath. So we can see then. So we can see this gives us a description of the data here. So we've got the name, we've got the number of observations. The size of the data set is just the number of variables multiplied by the number of observations in this case. And we've got 10 variables. So we've got all the variable names here. And again, these 2 bits are not really that interesting. It's just how the data is stored in the memory. So we're not really going to get onto the technical parts of this. And we've got the variable labels. So often when you're downloading data from online, normally the researcher will have given some labels to the data to help you understand what the labels mean. So we can see we've got age squared, years of schooling, real learning is 75, 78, and a no degree is a dummy variable for if they've got less than 12 years of education. So describe the data. The next command then is to summarize. So we know what variables we've got. So if you use a summarize command, then it will provide a quick overall review of some of the key statistics on the variables that we have. So we've got all of the variables: treated, age squared, education, so on. Number of observations, we can see then, so we've got the number of observations here. These could in principle differ if you've got an unbalanced data set. The mean, the standard deviation, and the min and the max. So you can, if you want, choose this. These are the default options. You can, if you want, include, say, the interquartile range and so on and so forth. So if you go into this data, if you look at this data manual, summarize will have this will be the default output. You can also then tailor this, and you can add in more columns, or you can reduce the number of columns if you want. Okay. So again, to graph the data. So firstly, the next command, and we can see here we've done two commands next, 5 and 6. So we can see there we've generated a new variable. So again, we give the name on the left, LW, and then we've defined it as the log of the variable RE78. So RE78 is the real earnings in 1978. Okay, so we've got the entry into the program in 75. So we're going to look at what's the effect on the future earnings in 1978. So this will be our independent variable. So we can plot a histogram to get an idea of the distribution of the data. So we just use the two-way. The next thing is to use the two-way function, which is plots a histogram of log of wages, and this if just selects LW, log of wages, for people that didn't have the treatment. And then Stator will open up a graph in a new window, and it plots it here. So again, this brings it out of Stator into a new graph, and again you can save this, you can edit the properties and so on. So we can see the mean is around 10, we get an idea of the width, the distribution, and so on. We can do now the same thing again. We can plot a histogram for the people that did get the treatment. And again, it plots a graph, it opens a new window. And again, if you want, you can plot two histograms on top of each other, and that's useful for comparison. And you can, if you look at the Stator manual, for the 2 is short for two-way. If you look at the two-way package, there's many options on how you can combine graphs, you can change the colors, and so on and so forth. But we can see by looking at it, remember now, treated means that they were put onto this very supportive training program. So really we should expect that people that had the training, it should have a positive impact on their earnings 3 years down the line. But you can see, just by comparing, this is the non-treated distribution, and we can see that it's actually shifted more to the right, namely it's higher, on average they're having higher income than the people that did have the training. So we can see the people that did have the training, the range is around 3 to about 11, and we can see for the non-treated it's around more like 5 to 12 here, and we can see that the mean of this distribution is higher. So again, this is just a rough plot, but it gives you already an idea that likely there's going to be some selection bias here. So we've just compared the unconditional distributions. So of course, we haven't controlled for any of the selection factors. So just because the distribution of, just because income for people that had the training on average was lower in the future than not in the unconditional plot, doesn't mean that once we condition all the selection factors, we'd then be comparing the conditional distributions, which in essence is what we're doing when we do the matching. But as a first off the bat, we can see that it looks like there's some selection bias here. People that had the training are earning less 3 years down the line, and this is because they self-selected, and the people that selected in to have the training program were likely less skilled and less wealthy and less well connected than the people that didn't apply for the training course. Okay, so that just gives us a rough idea then. We've got if you're doing a project, normally begin by looking at this, and then we go in and we will then start to make some more detailed analysis. So the next the next regression we've done is not because it's realistic, but let's assume that people only select into having the treatment based upon whether they're married or not. So the next command is to regress log wages on treated, namely did they have the training program or not, and control for a dummy if they were married or not. Now, it's unlikely that they would only select, it's unlikely to only select based on marriage. You'd expect people that apply for the program would also be selecting based upon their education, skill sets, their previous income, and so on and so forth. We're doing this as a comparison because we're going to work through manually by hand and derive the matching estimator when we just match based on marriage. So we're not saying this is realistic, we're just doing it as a comparison here. So we can see if we make all the assumptions we need in order for the regression to consistently estimate the causal effect, the crucial one being that when we control for marriage, the unobservable, everything that's left should be uncorrelated with the treatment. So this is unlikely to hold here, and we can see if we do this, we can see the estimate of the treatment effect is minus 1.12. Remember, this is in log points as well. So we can see this is saying that having the treatment program has led to a and again the t-stat is minus 18, so we can see it's highly likely. If you look at the confidence region here, there's a high probability this led to a significant reduction in earnings. Now, this is clearly not causal here. What's going on is that we've not controlled for all the selection factors that people were selected in order to get onto the treatment. Namely, they'd also be selecting by their education and their previous income and so on. So you can think of that as an omitted variable problem. We can see, again, the next part does the same thing. We'll just do the regression now, but with robust standard errors. So we're going to get the same estimate. We're just going to get the same point estimate. We're now just using the robust estimates of the standard errors. And we can see when we use the robust standard errors, we've gone from 0.06 to 0.081. So we can see that it looks like the default standard errors are biased. It looks like they're underestimating the true standard errors. But we can still see, if we did a t-test, the t-statistic is minus 14. We still have a confidence region which is significantly negative. Okay, so this is highlighting what we expected. Because these people self-selected into treatment, and it's unlikely that they only select treatment based upon whether they're married or not, then we'd expect to find a negative effect because the selection bias is negative here. Okay, so we can now then compare this with doing a matching estimator. Now you can there's actually a function in Stata which does it for you, and I'm going to show you that at the end. But we're doing this just as an example to show how we calculate it by hand and link it to the theory. So we want to now calculate the matching estimator where we're going to match only based on whether they're married or not. So namely, the idea would be then, we look at the difference between the treated and non-treated for married, and the difference between the treated and non-treated for non-married, and then average them back. If they only selected on marriage, then the people in the married group should have similar backgrounds, and therefore the difference between the earnings later of those that had the training relative to those that hadn't should reflect the causal effect of the treatment in that subpopulation. And likewise for the non-married people. Now this is unlikely to hold, but this would be the assumption. So what we have to do is that the matching estimator here, we just need to work out, well, what is the treatment effect in each subpopulation, and then weight them by the probability of being in each subpopulation. So we can now use the next function to get an idea. We can use a tabulate function. So this is short for tabulate. We're going to do a table with married on the left, treated on the right, namely training program or not, and then summary, namely we want to summarize the log wage. And no standard just means do not plot the standard errors, because we're not going to need them here. So this would be our xi, our control variable. we've got married or not, and we've got our treatment DI equals 0 and DI equals 1. So this gives us a lot of key information here then. So we can see each of these quadrants. Take for example quadrant 1. Well, quadrant 1 is going to be the estimate of the expectation of Y log wages given they're not married and they don't have the treatment. So it's an estimate of this. So E is the population value, and this is going to be the sample estimate. And likewise, quadrant 2 is going to be the estimate of E of Y log wages given they're not married and they had the treatment. And we have the number of people in each group. So there's 291 people that are not married and didn't get the training, and so on. Okay, and we can go through. So quadrant 3 is just going to be the expectation, an estimate of the average log wages given they're married and they didn't have the treatment. There's 1,913 people there, and the final quadrant will be the estimate of the log wages given they're married and they have the training program, of which there are 44 people here. Okay. Again, these are population. These are the sample estimates of them. So we have a sample estimate of the average wages given them not married and they're not treated as 9.543, and there's 291 people in that category. Okay, so this is key then. So then we can see straight away we've got an estimate of the treatment effect within each subpopulation. All you do is subtract one from the other. So we can see here, we just subtract this from this and subtract this from this. So we want the other way around. We want the treatment we want to subtract the treatment effect for the non-married people is 8.49 minus 9.54, and the treatment effect in the married population is just 8.62 minus 9.995. And we can see that it's negative. And again, this is because the selection bias likely remained. The people that had the treatment, even though we're controlled for marriage, it's likely that they're also going to be selecting based upon education and so on and so forth. So we already expected this from the regression above, that we're going to find a negative treatment effect here. Okay. So next we want to get we can calculate the treatment effect now. Well, the average treatment effect. So going back to the lecture notes, he gave the formula for this. So the average treatment effect in this case, well, it's going to be what? Well, the population. We want an estimate of the population average treatment effect. So again, if you go back to the lecture slides, we have, well, the average treatment effect is just E of, well, we're going to have Y1I minus Y0I. So this is here, this is income for the people at the training program, and the other one is potential outcome for people that didn't have the training program. And we're now going to break this up into two parts. Well, it's just going to be the expected value of Y1I minus Y0I given Xi equals 1 and Di equals 1 times, so we're going to get so we're going to get it's going to be the average expectation of, well, it's going to be the treatment effect in each subpopulation. So we're going to get the expectation of Yi given Xi equals 1 and Di equals 1. So let's start with the married population minus the expectation of Yi. Again, match like for like, so we're going to compare married but now people that didn't have the treatment. So this is the treatment effect within the married population, and we're going to weight that by the probability that Xi equals 1 plus then the treatment effect in the non-married population. So it's exactly the same now, but we just compare the means for the non-married people for the treatment and the non-treatment. So it's simple here, there's just two categories. It's going to get more complex as you start adding more categories. Times probability xi equals naught. So we can see in each case, this is just the treatment effect for the married population. This is the treatment effect for the unmarried population. And these are just the weights. This is a probability that we're in the married population. This is a probability we're in the unmarried population. If we average them back, we're going to get back to the average treatment effect in the whole population by the law of large numbers. So all we need to do now is estimate these. So we go back to the table and we can pick out the elements. So again, we've already labeled these previously. So if you go back, we can go back. If you look at the table, if you've got your notes with you, well, we just got the 4 quadrants. So to begin with, then, so we want to take the sample estimate. So call it ATE hat. So we just replace these with sample estimates. Well, what's the mean of income for the married and treated? Well, it's 8.49999, and subtract what's the average income for the married and no training is 9.544, and we want to multiply that by the estimate of the probability. Well, what's the probability that they're married? If you go back, it's just the proportion of married people. So it's 477 divided by 2,434, and then likewise we're going to add the treatment. We estimate the treatment effect in the non-married. Well, the non-married. Sorry, that was a non-married. That was the non-married population. We're now going to do it in the married population, which will be the average income for not married and treated is 8.6211 minus the average income for the married without the treatment, without the training, is 9.51, multiplied by the proportion of people that are married, which is 1957, divided by 2434. So we can get all of this information from the table previously. We've got all the conditional means in each subpopulation that have the treatment and don't have the treatment, and then we can weight them by the probability of observing this. And we find this to be minus 1.2737. So we can see that the estimate of the average treatment effect is quite similar to the OLS estimate. So the OLS estimate of the treatment effect was minus 1.1223. So we can also see that this bias has remained, the selection bias has remained even with the matching estimator, because the crucial assumption for the matching estimator to work is this unconfoundedness. Namely, the crucial assumption for both OLS and matching is that once we control for these selection factors, then there's nothing else left that they select when they select into treatment. That everything else that's left is exogenous. And in this case, of course, just matching people based on married and not married is obviously not going to be all the selection factors. Okay, so we've got the estimate. We can now work out the standard error. And that's what the next two graphs look at. Well, what's the formula for the standard error? Well, we can, again, as from the previous lecture, it depends which assumptions we're willing to make. The average treatment effect, the general formula for the, let's write it in the, we've worked it out for the particular example at hand, but the formula in general for the ATE in this particular example, well, it's just the proportion of people that are married, number of people that are married, M1, divided by total people, times by the average income of married people that are treated, minus y bar 1 naught. So this y bar 1 1 is just an estimate of this, and y bar 1 naught is an estimate of this. So it's a difference in the means of training and non-training for the married population, plus n naught, so number of non-married people times divided by total number of people, and then the estimated treatment effect within that population. So y bar 1 naught is an estimate of this, and y bar naught naught is an estimate of this, and these are the sample proportions of the probabilities of being in each quadrant. So this here we've just estimated for our particular example, but this is a general formula when we just match based upon one dummy variable. So the standard error, if we assume we have an IID data set, then the covariance between these two should be naught, in which case we can just take the variance of this will be the two variances added together. So call this P and call this 1 minus P. We're just going to get P squared times the variance of delta hat 1 plus 1 minus P squared delta hat naught. So just to make it simpler to write, just redefine this here as P, define this as delta hat 1, this would be 1 minus P then, and this would be the delta hat naught. So, and then we take the square root. So all this, assume we've got an IID data set, then the variance of the sum of the two terms is just the sum of the two variances added together. Okay, so we've already got the sample proportions above, so P is just this term here, and 1 minus P is just this term here. We now need to work out these variances of both of these treatment effects. So that's what we need to work out the variance of the difference in treated and non-treated for married, and the same for non-married. So to get that, we can then go to the t-test. We don't want to do a t-test, it's just that this operation will give us the standard errors of the difference between the average income for treated and non-treated. So if we use a t-test function, so if we look here, the next part then would be to run this. So it's a t-test. It's a t-test on log of W for people that are married, and we're going to do the test by treated. So namely, if we wanted to do a t-test of whether the average income of treated for not, this would give us a t-test here of the hypothesis that the income for the treated and non-treated was the same for married people. Okay, so we don't want to do that, but what we do want to do is get out some information from this table. So again, this just repeats some of the above. So this here is the group for treated and non-treated. It's plotting properties of the log of the wage, and it's for people that are married. So we can see these here are just taken from the table before. Here. For the married population. So we can see we get these again, look here. So all it's done, again we'd expect to get these. All we're doing now is going to give us the standard errors. So in this case, we want the standard error of the difference. So this difference is the difference between these two here, which is what we want. Again, we difference it the other way around, but it'd be negative, but it's still going to have the same standard error. And the standard error of this difference is 0.108856. And this has done it assuming equal variances. If the variances are not equal, you'd have to use the robust standard errors, and you can look at the Estimator. The lecture slides from lecture 2 gave an example of this, of the formulas, and it's also mentioned in Angrist and Pish. The formula for the standard error simplifies if the true variances in each subpopulation are equal. If they're not, then you have to use the general formula. Okay. And then we can do the same thing for the non-married population, which is next. So here, and we want the same things out again. So we want the difference, we want the standard, again we want the difference the other way around, but again it doesn't matter. We want the negative of this, the variance will still be the same, and the standard error is 0.09710. So we can now plug these into our formula. So if we go back to the formula for the standard error, Well, we just plug everything in. So P, so we're just going to get, well, the proportions is 1957 over 2434. So this is the proportion of married people times by the standard deviation of the difference in the treated and non-treated income for married people, which was 0.0186. And we're going to square this because this was the standard error. So if you go back, this was the variance in the difference of the means for the married population, and it's a standard deviation. So to get to the variance, we square it. And we do the same thing for the non-married population, where there's 477 non-married people out of 2,434, and the standard error of this mean difference was 0.00917 squared. And we can find this roughly equals 0.089. So this is given in the handwritten notes. If you look at the handwritten notes in the week 1 folder, it actually runs through all of this. We're just doing it again here to give a bit more detail and background into the handwritten notes. So hopefully that's clear, and again you'd be expected to calculate, in terms of exam type questions, you'd be expected, given the requisite output, you'd be expected to be able to calculate these things. Again, the example would have to be relatively simple, namely there can't be too many matching factors, otherwise there'd be too many elements to calculate. But this just runs through how, hopefully it gives you a bit more of an idea of why this works and how we calculate these the average treatment effects and how we work out their standard errors. If you're doing this for a dissertation or an empirical project, of course you can just use the generic Estimator functions. There's a Estimator function that actually estimates that for you automatically, so you don't have to do it all by hand. Okay, so the next part just shows you, okay, well, we can see then, using both matching and regression on using selection just on marriage, they both give a similar estimated treatment effect of around -1.1 to -1.2. So we can see this is likely to suffer from a selection bias. We would not expect that the training program would lower people's incomes later on. So we could try control for more selection factors and variables, especially around their age and their education, and whether they've got a degree or not. So we can see, if we try to estimate the treatment effect using the regression approach, once we control for more variables, which may be selection factors into treatment, we can find that the estimated treatment effect is now still negative, but it's smaller in size than previously. So we can see here that some selection bias still remains, but we can see the estimated treatment effect just based on marriage was -1.124. Now it's gone down around 0.5 in absolute size. So we can see then that although it's likely that there's still some remaining selection factors that we've not controlled for, this could be things like their previous income, it could be things like whether they've been using drugs in the past, whether they've been to prison, and so on and so forth. All these other factors which, once we control for them, we may then find that there will be a positive effect of the treatment. Okay, finally then, let's just do a final comparison just to show you how we can use Estimator's inbuilt treatment effect estimator. So suppose now that we just want to match based upon marriage, whether they're married or not, and whether or not they've got a degree. So the first output gives you this. We can see here the treatment effect in this case, if we just control for marriage and degree, is still negative, but it's about -0.92. We now want to compare this to the treatment effect estimate using matching, so we can use the TE effects package. And again, there's some, if you the Estimator notes on this and user guide are actually very clear and useful. So the T effects, the package in Estimator, we're going to use the NN match module. We're going to match the independent variable log of wage. This here is the treatment, whether or not they had the training or not. And this E match means we're going to exactly match. So that means we're going to exactly match like for like people. So in essence, we're going to get 4 categories. We're going to get married and non-married, and we're going to get degree and no degree. So we've got married, non-married, degree, and no degree. So you're going to get 4 categories now as opposed to 2. And what this is, we did it before, just married and non-married. We got the treatment effect in each subpopulation and then weighted back. Now we're going to get a treatment effect in each one of these subcategories, and then we're going to weight them back. So this would take obviously a long time by hand, but this package does it for you automatic. Okay, so we're going to exactly match, and again, what we can find, the treated have the training versus not, the effect is -1, around -1. And again, this is similar to the OLS estimate here. What do we notice is that the standard errors are significantly higher than in the OLS case, and we expect this because, as we mentioned in the lecture, in general, the matching estimator is more robust to things like non-linearity and non-constant treatment effects. The downside is that as you include more categories, the number of people within each category gets smaller, and you're going to get a poorer estimate of these treatment effects in each subpopulation. Okay? The reason why, just to be clear and to finish on here, the reason why I didn't give you a matching estimate matching on all of these is because it doesn't exist. And the reason is age and education and these race indicators and no degree, there's just too many subcategories. If you've got years of education there, say 1, 2, 3, 4, 5 to say 15, you've got age, which can go, it's done in years, so it would go from say 18 to 60 or whatever. So if you think about that, there's going to be hundreds of categories. And in that case, if you try to exactly match, you cannot do it. And the reason is that when you try to exactly match here, because there's only 2,700 observations, there simply isn't in each possible category of person for age, education, and marriage and so on. In some of the categories, there will not be people that did and didn't have the treatment. And in which case, this is what's known as the overlap assumption, as we talked about in the lecture. The overlap assumption just says we have to assume that within each possible subcategory, there's somebody in the treated category and somebody in the non-treated category. Now, you can get around this by using other methods which we haven't covered in this course, but the idea is, and it's talked about in there, if you want to look at this for yourself, if you can't exactly match, then you have to make some more assumptions, and what you would do is you'd match people that were kind of quite similar, and you'd use what's called the nearest neighborhood matching, where it may be that you'd have to have people that say have got education, say within 1 or 2 years of the other person and so on. So if you weaken the requirements a bit, you're not exactly matching, you're just matching people that are quite similar, and then you've got to increase the assumptions that you make. You'd have to assume that just matching on people that were quite similar would get rid of all the selection bias. So we're not going to cover this in this course. I just want to make it clear to you that this exact matching, although if it exists, it can be very robust. The downside is that it's very difficult to exactly match, especially with small sample sizes, for the simple fact there will not be enough people in each subcategory with which to estimate the treatment effects within there exactly. Okay, so we finished up for that there. So I hope you find that useful. I mean, I also plan to do another session on going into a bit more detail on some of the formulas behind the cluster robust standard errors. So I ran out of time a bit towards the end of the last lecture. So I'll do a bit of a summary, and I'll recap the points, and we'll go through the 4 different methods, and we'll do the pros and cons and give a bit more formal background. So hopefully that will help. And I'll send out tomorrow the exercise sheet for next Friday and also the lecture slides. Okay, so I'll see you all next Tuesday.